Hi, everybody. Thanks for joining us today. Today's session is on stars, disk, and planets. The first of two sessions on stars, disk, and planets. The next one is at 11 a.m. In this session, we have four speakers lined up. Our first speaker is Rachel Osten from the Space Telescope and Science Institute at Johns Hopkins University, who will be talking to us about predicting the past to understand the future, the context of time, and considering habitability. And I remind you all to use the Q&A feature to enter your questions whenever you have them. Thank you. Rachel, take it away.
Okay, thank you, Rudy. Let me start sharing my screen. And let me find the play button. Okay, all right, great. So you should all be able to see my front slide.
Yes.
And yeah?
Yes.
Okay, great. And I'd like to take this opportunity just to thank the organizers for inviting me to speak at this Chandra Frontiers in Time Domain Science workshop. Between coronavirus and Astro 2020, this has been quite a year, but fortunately, as you can maybe see from the virtual background, I've been quarantined with a flare star. So this is appropriate for the talk, the text of this talk. So I was asked to talk specifically about flares in the context of habitability, and I've tried to do that, highlighting some of the progress that we have made in what we know about flares and what the sort of big open questions are, especially regarding what happens to the near stellar environment. Okay. So the main point of this is that stars influence the planets that are around them. They influence their near stellar environment. There are stellar astrophysics questions, which I've listed here on the left, taken from an Astro 2020 white paper. And each of those stellar astrophysics questions, interesting and important in their own right, have implications for habitability. So I'm not going to be able to talk about all of these. There are some excellent talks coming up in this session and the next session that will address particularly interesting aspects of young stars. So I'm not really going to touch on that, but I'll try to talk about what factors control the coronal emission of stars and why you might be interested in that for the star planet considerations, and then talk about flares and stellar winds and how those change with time, why we want to understand those. So the basic talk outline, talk about what we know about flares and flaring stars somewhat briefly, and then talk about what we still need to know and why this is important for the near stellar environment. So there's one point that I like to drive home whenever I'm talking about high energy emission and stars, and that is something that I think is recognized by a subset of astronomers, but there's many people, including the public, who still think of X-ray astronomy as the domain of black holes and compact objects and, you know, exotic types of matter in our universe. And this is it's a little bit of an old plot now. This is X-ray detected stars pre-Chandra, but it illustrates a very nice point, and that is that X-rays are a normal part of the day-to-day business of a star being a star. The fact that you can see a main sequence here nicely delineates X-ray emission from O and B stars all the way down to the coolest M stars. So this shows that these are not weird stars. Of course, you can have emission from compact objects, and those are the subject of different sessions at this workshop. But this is a point that I like to drive home. So that's an X-ray HR diagram. Going more specifically to the subject of this talk, This is a flaring HR diagram. And this is another point that if you take nothing else away from this talk, you should remember this, that flares are a fact of life for cool stars on or near the main sequence. Now, this is an ensemble of flaring obtained using white light flare studies from the Kepler mission. But again, you can see that there's a main sequence clearly delineated. Of course, there's a bias in what kinds of stars were targeted by the Kepler mission. And the flare activity is notable for stars that are a little hotter than the sun, all the way to the coolest M dwarfs that were targeted with Kepler, and even some slightly evolved stars as well. So flares are a fact of life for cool stars. Our expectations for flares from the sun, that our expectations are that they occur in loop-like structures above active regions. This is a movie from the Solar Dynamics Observatory showing some beautiful, spatially resolved arcades of flaring loops that are moving as the sun is rotating. They are dynamic, they are interconnecting. There's brightenings that are occurring stochastically. So this involves the liberation of energy, part of which goes into heating of plasma to temperatures above the quiescent value. You can see that even outside of these flaring regions, there is brightness that comes from non-flaring coronal emission. And the dynamic nature here reveals that there's a lot of motions involved, rearrangements of magnetic fields. So this is complicated. Magnetic reconnection is inherently nonlinear. When I talk about results for particular types of stars, the goal of always is to understand processes in a very general sense, but we don't study the universe generally. We study the universe by targeting, studying specific events. And so there's a bias in the types of stars that are typically targeted for flare studies, and that will show up in the specific instances of stars that I mentioned later on in the talk. There's young stars which are rotating rapidly by virtue of the fact that they're young, and their fast rotation, because of the rotation activity correlation, means that they have enhanced magnetic activity, including flaring. Active binaries are some of the most extreme examples of magnetic activity, and they exhibit this extreme activity because of their enhanced rotation. So again, this is all due to that fundamental rotation activity correlation. And these two stars, typically one is an evolved, a subgiant or a giant, and the companion can be a main sequence or an evolved star. These are interacting magnetically. They're not transferring mass, but they are close enough that their orbital and rotational angular momentum are locked, and that enforces fast rotation. Rotation activity correlation shows that they are examples of extreme magnetic activity. And then the fully convective M dwarfs have very deep convective zones. They are able to generate very frequent and very extreme flares. And so that's the sort of third general category of usual suspects when you hear about flare studies. Okay, so flares involve the creation of hot plasma. This is a paper showing some Chandra results on an active binary system, Sigma Corona Borealis, where you can see the exquisite power of the Chandra high energy transmission gratings, where you can access both the numerous lines as well as the continuum emission here. The plot on the left just shows a spectrum extracted during quiescence and another spectrum extracted during a flare. And the differential emission measure distribution in the plot on the left just shows that during the flaring emission, there's the existence of much hotter plasma, temperatures above 30 million degrees, compared to what was visible during the quiescent interval. And this is reflected in the shape and the level of the continuum emission that you can see over on the right, where all the line regions that regions that contain emission lines have been masked. You can see the shape of that continuum lends credence to that higher temperatures, as well as enables you to do abundance determinations. Flares often also show coronal abundance anomalies. And that could be a whole talk unto itself, but I won't go there. Some of the key parameters when characterizing flares are what the radiated energy in the flare is, what the peak X-ray luminosity is. In some of the most extreme cases, that can exceed the bolometric luminosity of the star, and the peak temperature. The example I showed has temperatures that go up to a few tens of millions of degrees. Some of the more extreme flares can have temperatures exceeding 100 million degrees. Right. Flares also involve mass motions. This was a recent paper from a flare observed on a single evolved FK Comey type star, where they subdivided the flare light curve into some different time intervals. This is showing, the top panel shows the light curve in a different line. So magnesium 12, the left and middle, and then on the right, oxygen 8. And then the colored spectrum corresponds to the dot, the appropriate dot on the light curve. And then the bottom panel shows the velocities implied from fitting two Gaussians to this spectrum, and then looking at the one that is offset from a zero velocity. So there is some evidence for blue shifts and red shifts during this flare, and I'll come back to this a little bit later. So studies of the overall extreme X-ray, extreme ultraviolet flux with time show that it's important for close-in planets. This is a paper from Johnstone et al. In 2015, who did simulations for an Earth-like planet around a sun-like star. And the first plot to look at is the one in the upper right, showing the dependence of the hydrogen loss rate, the exoplanet atmosphere, as a function of the incident extreme ultraviolet X-ray flux. So the two are correlated. The higher the XUV flux, the more the atmosphere can be lost. And what these scientists did was do some simulations where they started at an age of 10 million years, went up to 1 billion years, and they had two different scenarios. One is, so there's this rotation activity correlation. They had two scenarios. One is the XUV flux versus time for a fast rotating star, and the other for a slowly rotating star. And then they captured the impact of that for the two different rotation cases at two different time snaps. And that's what's shown in the lower right. So these are contours of the fraction of the atmosphere of the planet by mass. So that's what FAT is. And in these four cases, you can see very different outcomes at the two different times as to whether the planet can keep its atmosphere or not. The white regions on the lower left are the situations where the entire atmosphere is lost, and then the very dark red regions in the upper right are where the entire atmosphere is kept. So clearly it's important to have an understanding of what the evolutionary history of that star-planet system has been in order to evaluate what the consequences are for whether this planet might have be able to keep its atmosphere. There is emerging evidence that stellar twins may not be magnetic twins. So this is very interesting, because we usually think of, fundamental properties of a star. You'd like to be able to predict as much as you can based on those fundamental properties. So this is an example, Gliese 65A and B, which have nearly identical spectral types, masses, radii, rotational velocities, rotation periods, metallicities, integrated magnetic field strengths, And yet when you investigate what the distribution of surface magnetic field is on these two stars, you get very different results. In one case, you've got a complex non-axisymmetric field. And in the other case, you have evidence for a more axisymmetric dipole. These two stars do display differences in their magnetic activity. One tends to be more variable and flary than the other one. And that is demonstrated over here on the right, showing the different magnetic field breakdown in the two stars, Gliese 65A and B. And for comparison, there's a higher mass binary YY gem that has nearly identical stars, and they do show some similar magnetic topologies. So the plot on the lower left shows the X-ray luminosity as a function of rotation period. This is the rotation activity correlation that I've mentioned. This is a more updated version for M dwarfs in particular. And you can see that there's a pretty sizable spread at any given rotation period. My collaborators and I have a current Chandra program where we're investigating the coronal properties of M dwarf twins. So these are wide binaries that have masses to within a few percent, measuring rotation periods, measuring optical evidence for magnetic activity, and then we can hopefully try to calibrate this plot a little bit better by removing some of those other parameters like age, mass, and radius, and then see what the impact of intrinsic magnetic activity is in shaping this plot. So solar eruptive events come in three parts. There's the solar flare that I've talked about already, but those are often accompanied by solar coronal mass ejections and solar energetic particles. That's the fuzz that you can see on the coronagraph movie on the right. And while the flare is the easiest to see, the CME and the energetic particles are more impactful. They're in the solar context, they're called geoaffective because they can impact the Earth more. But there are complexities to this because while the radiation from the flare is isotropic, the impact of the CME and the energetic particles really depends on where they happen on the sun's surface and where the Earth tends to be in its orbit. So it's a more trying to extract this to an exoplanet case requires a more probabilistic approach. And this I thought was just sort of interesting to note the rise in interest in what I call exospace weather. Just doing an ADS search on refereed papers mentioning both exoplanets and space weather since 2000. And I didn't do it, but I could fit an exponential to that and predict when it will take over cosmology. Maybe someone can do that in the who's looking at the talk and give me the answer in the question, the Q&A period. Okay, so this exospace weather and habitability really depend on stellar magnetic fields and eruptive events. This is a caption, this was actually the cover of a Science article talking about the impact of interplanetary coronal mass ejections on Mars, which may have been instructive in Mars losing its atmosphere. The star's magnetic field creates an ecosystem that helps to set the environment that planets and life experience. That can even influence the inner edge of what we've called the traditional habitable zone, showing that there's complexities there in terms of how stars and planets interact. And as I mentioned before, the coronal mass ejections and proton events have the biggest impact in determining the effect of reconnection events on planetary atmospheres. We don't really have many observational constraints in the stellar case, and it requires scaling from the sun. So it really relies on a very detailed interplay between solar physics and stellar astronomy. This is a paper just demonstrating that fact. So this is an astrobiology paper who simulated the effect of a powerful flare from an M dwarf on an Earth-like planet in the habitable zone of that M dwarf. And when you only consider the effects of electromagnetic radiation, the plot on the left shows very little fractional change in the ozone column with time. The bar goes down to 0.01, so it's a % change at most. On the other hand, if you include the effect of these energetic particles, which would happen in the CME, flare CME eruptive event scenario, you can see much more significant impacts. I mean, so the bar now goes down all the way down to 1, meaning that the ozone, not just an ozone hole in the atmosphere of the star, it's an actual depletion of that of the ozone from that exoplanetary atmosphere. So but that requires scaling and requires understanding that scaling is applicable in other stars. So I want to talk about different observational techniques that we can use to try to observe stellar CMEs. One is trying to use coherent radio emission, using a new generation of low frequency radio telescopes to detect something called a type 2 burst. These originate from coronal mass ejections, not flares. And this was work that a PhD student of mine did and published a couple of years ago, where we expect that there to be a high association rate between flares and CMEs, as is seen on the sun. We know that for the very fastest CMEs, they produce MHD shocks when the velocity exceeds the Alfvén velocity, and that produces this type 2 burst, which has a very characteristic shape in frequency and time. And so this was a very nice potential diagnostic because it could enable us to see the CME itself and not just some, interpretation of a flare. And it could potentially allow us to diagnose some basic characteristics of the CME. So what we saw optical flares without any evidence of something we could interpret as a type 2 burst. We had some interpretations. There's always the fact that we could be unlucky, the universe could be cruel. If there's a mismatch between the type 2 parameters and the observing sensitivity, we could just have been unfortunate. There's the other possibility that the shock, that the velocity could not have exceeded the Alfvén speed, and therefore no shock would have been produced and no type 2 burst would have occurred. And so we had actually, although we did not see what we wanted to, we had 64 hours of observations. And so we could place pretty robust constraints on the occurrence of these CMEs, subject, of course, to some of the caveats that I laid out already. And this was around a very nearby, highly active pair of M dwarf stars. Should have mentioned that. So thinking about some other possibilities of stellar CMEs, there's
recycling bin.
Go. No.
I'm giving him a recycling bin. Mommy. Mommy, no.
There's absorption dimming,
No.
where the flaring, you've got the flaring loops, and then there's a temporary increase in the absorbing column as material covers the flaring region. There's mass loss dimming, where you can have a decrease in emission due to the ejection of mass. Paper by Louise Hara et al. Suggested that these dimming signatures may be the best way to search for stellar CMEs. This is an example of the mass loss dimming from the sun, showing iron ionization light curves for a solar eruptive event. And this illustrates the power of having access to the extreme ultraviolet portion of the spectrum. Each panel here is a light curve of a different ionization stage of iron, from iron 24 in the upper left, iron 22, 21, 18, 16, and then all the way down to iron 9 in the lower right corner. And you can see that the shape of the light curve changes as you transition from diagnosing the very hottest plasmas, where it's clear that the flare is acting, to the coolest plasmas, which are more characteristic of the quiescent emission from the star.
3 minutes.
Okay, thanks. And that sort of decrease below the 0 line, where that's the average before the flare or eruptive event, is the signature of that mass loss dimming, where it's a coronal mass ejection. That mass has been ejected and you have less emission as a result of it. Recent studies by Meng Jin have shown that this signature may be observable in magnetically active stars. And in fact, this escape mission, of which I'm a co-I, is a SMEX concept that's been accepted for a phase A study. We may actually be able to observe this in magnetically active stars. The absorption dimming has had some traction recently in stellar applications. And this was a paper a few years ago by Sophia Moscou showing an interpretation of a previously reported column density variations in a giant flare on the active binary Algol. And they interpreted this as a smoothly expanding CME, basically the increase, the temporary increase and then decrease in the column density due to this obscuring material overlaying the flaring emission. Constanza Argirafi, this is the same light curve that I showed earlier, has presented evidence for blue shifted material in cooler plasma at the end of this flare. That's basically the blue filled circle on the bottom rightmost panel, which appears to indicate a significant blue shift in this very cool coronal plasma as evidence for plasma motions in a CME. So there's some complexities to whether stellar events can erupt. So on the one hand, the radio observations did not appear to show any evidence for stellar coronal mass ejections. There are some scattered claims of CMEs in mostly these very magnetically active stars. And there's a question of whether magnetically active stars that have a high flaring rate also have a high rate of coronal mass ejections. So some recent work by Alvarado Gomez et al. Took a look at this from a modeling perspective. And these are 3 snapshots of different scenarios where they had a weak field. Weak is plus or minus 600 Gauss, which is still pretty strong. An intermediate magnetic fields case, that's the middle panel, which is 1000 Gauss. And then their strong field case on the right, which was 1400 Gauss. And so they set up this magnetic geometry, let it go, and then watched to see if a flare event could escape or would be confined. And they found that in the intermediate and the strong field case, the magnetic field can have a suppressing influence for moderately active M dwarfs. So that suggests that there's a little more complexity to just taking the solar case and extrapolating up to very energetic flares for these different stars. So I think I may end more or less on time. So I'll end sort of where I started. With questions that really beget more questions. So these are those 4 stellar astrophysics questions I laid out at the beginning of the talk. And then I've transformed those into questions in the context of habitability. So like I said, I didn't really talk about the first one, but what factors control the coronal emission of stars? How well can the coronal emission be predicted from its other fundamental parameters? Is this a function of stellar age? How do the characteristics of flares change with time? we'd like to know in a systematic way, what are the maximum energy, the maximum luminosity of flares, and how do those change with time? Another topic I did not have time to get into is how do accelerated particles act during flares? And the final question of how do stellar winds change with time? We want to have more robust observational tools to assess the systematic behavior of coronal mass ejections, and then start to investigate how that is might be different for stars of different stellar types and different ages. And I will stop there.
Thank you, Rachel, for a very thorough and really interesting talk. And I noticed that there's so many, a lot of the papers you were talking about were very recent work. So recently in the last 2 years, which really shows that there's a lot of progress being made in this field, I think. We have 2 questions. The first question, and these are both on the stellar twins phenomenon that you alluded to. The first is from Moritz Guntner, who says, could it be, with respect to that stellar twins are not magnetic twins, could it be that we are just observing the 2 different stars in different phases of their cycles? Our sun can look very different if we perform observations that are just 5 years apart.
Yeah, and that is one of the questions that we would like to be able to address, right? We know that stars change and that they're dynamic, and so how much of this scatter in X-ray luminosity is due to the intrinsic activity of the star, different phases of a cycle, and how much of it is due to that astrophysical rotation activity correlation.
Another question on the subject is, I imagine that there are not available data to probe any magnetic cycle in those stellar twins with different X-ray properties, correct? And this is from Mario.
Can you read that again? There are not
data to probe the magnetic cycle in those stellar twins. So I guess long-term.
Yeah. So I should have elaborated on that a little bit more on this slide. So, and I should also say that we got our first Chandra observation on Saturday. So I apologize, I don't have the paper written yet. but the data do look beautiful. So the Chandra observations are actually part of a concerted ground-based effort to get the rotation periods, to look at those evidence for magnetic cycles, and do that kind of. So the data does not exist yet, but it is being obtained, I would say.
And I guess I'll read this question and go back to Mario's. This is from John Miller. Great talk, Rachel, as always. If Chandra continues for another 5 years, will the field obtain answers to your final 4 questions? Do you need changes in observing scheduling or constraints, e.g. are long stares required, or is it total exposure the key quantity?
So let's see. So if you gave me all the time on Chandra for the next 5 years, then I could probably go a fair way towards answering some of these questions. Some of it depends on collected exposure time. Some of it depends a little bit on, I don't really want to say luck, but since flares occur stochastically, you cannot necessarily predict when they're going to happen. For addressing a question of this coronal emission, can it be predicted from its other fundamental parameters? I think that's one area where, I mentioned the specific program that we're doing, which is small at this point, but in, right now and in the next few years, there's this stellar renaissance, right? With Gaia producing, constraints on parallaxes, distances, being able to just really have a much better understanding of some of the other fundamental properties of stars, coupled with space missions like Kepler, K2, TESS, where you can start to get at what the rotation periods of many of these stars are. They're not it's not a panacea, but it's making a significant headway. Then I think you could, with well-designed observing plans, target some of the nearest stars and use that increased precision of the other fundamental parameters to help with understanding the coronal emission and its impact on systematics and age.
Great. And the last question, we have about 45 seconds. What is the expected or predicted rate of flares that can impact the atmosphere, such as those that you have shown us?
The astrobiology papers tend to focus on the most extreme flares because they don't want to see if that is going to have an impact. Let me go to this paper right here. So this Tilley paper actually looked at a range of different flares over 2 orders of magnitude, roughly a little less than 2 orders of magnitude in radiated energy. And you can see that obviously the most extreme flares have the most extreme response, but you're still seeing significant impacts even for the moderately active or energetic flares. But again, it goes that goes to the scaling with of the electromagnetic radiation with energetic particles.
Great. Thanks so much, Rachel, for an excellent talk. Our next speaker, I'll ask them to just prepare their slides, is Stephen Chen from George Washington University. And they are going to talk to us about variable X-ray sources in intermediate age open clusters. Stephen, can you share your slides, please?
Yes, hello?
Yes, perfect.
Okay, cool. Good. Okay, so my presentation is on variable X-ray sources in intermediate age open clusters. So we've looked at 2 of these clusters so far, NGC 3532, a 350 million year old one, and Trumpler 18, a 25 million year old cluster. We looked at multi-wavelength observations conducted by Chandra, Gaia, 2MASS, and WISE, and we matched Chandra sources to their multi-wavelength counterparts within 1 arcsecond. We determined variability on short time scales with the Kuiper test probability statistic. And here's the Chandra X-ray images of both clusters. So here we have the HR diagram of both clusters. So we see all Gaia field objects in black. We see Gaia cluster objects as determined by a rough distance cut in cyan. And we see X-ray sources on the red-yellow color scale. The color corresponds to Chandra hardness ratio, and the size corresponds to Chandra broadband flux. And we also see variable X-ray sources marked with an asterisk. And we see that there's a concentration of these variable sources near the bottom of the HR diagram in both clusters. So these are likely lower mass stars with active corona. And as well, we also have a few other sources. This source, for instance, is likely a late A-type star, and this source near the red clump is likely an evolved massive star in a binary. So here we have the hardness ratio diagrams of both clusters. We see that most of the variable sources marked with asterisk have multi-wavelength counterparts, and that the variable sources tend to be harder than the non-variable sources on the medium-soft hardness ratio scale. And we also see that Trumpler 18 tend to have harder sources, variable and non-variable, than NGC 3532. This might be due to an absorption effect. And overall, we see that about 25% of Chandra sources do not have any multi-wavelength counterparts, and they tend to be concentrated toward the harder end of the plots. So we've also conducted a supervised machine learning classification of the sources using multi-wavelength data. And so out of the few hundred sources in both clusters, we have classified a few dozen of them with greater than 70% confidence. And as expected, we see that most of the sources are stars. We also have a few AGNs in the background and a few young stellar objects.
2 minutes.
So yeah, so here's my conclusions. Most importantly, we see that multi-wavelength analysis of these X-ray sources is a powerful tool for classifying them. And that's my presentation.
Thank you, Stephen. Thank you for a really interesting talk. If we have any questions from the audience, please enter them into the Q&A box. If not, I have a question about why do you think these sources are harder? These variable sources are harder. These are probably most likely binaries.
Yeah, they might be. So we see that they're harder on the medium soft hardness ratio scale, but not necessarily on the hard medium
Okay.
hardness ratio scale.
And do you have any plans for pinning down those unidentified or sources without corresponding multi-wavelength components?
Yeah, so we'll be looking at all of these sources in more detail as part of my ongoing work. And we'll also be looking at more clusters.
Awesome. Great. If there's no further questions, then we will move on to our next speaker. Thank you again, Stephen Chen.
Thank you.
Our next speaker, if you can start sharing your slides, is Thomas Ayres, and coming to us from University of Colorado, and is going to talk to us about cycles and the 7 dwarfs.
Thanks, Rudy. So I'm going to tell you about a program that I've been carrying out for a number of years now to observe magnetic cycles of late-type stars, dwarf stars mainly, at high energies, and that's using Chandra to capture the coronal X-rays and 2 UV spectrographs on the Space Telescope to capture the far ultraviolet region of the spectrum, which is associated with the X-rays. The camera we use on Chandra is the HRC. It has good soft sensitivity. It's immune to optical loading. It has high spatial resolution, which suppresses the background, and also allows us to observe relatively close binary systems, and has a large field of view. And in this work, which started back about 15 years ago, we've been concentrating on binary systems that fit within the field of view of the HRC. And that's important for these monitoring programs where we capture observations at roughly 6-month intervals of these systems from an efficiency point of view. So we started off with Alpha Centauri, the famous nearby system with 2 sun-like stars. We moved on a few years ago to Procyon, which is a mid-F subgiant. And most recently, we've gone to 70 Ophiuchi and Xi Boötis, which are binaries of basically later type stars. And that work has just begun. Here's some results. In the top of these 4 panels, we show X-ray light curves over about a 15-year period for the sun, Alpha Centauri A, Alpha Centauri B, and now this newest one, Procyon. The lower curves here are ultraviolet emission lines captured with a Space Telescope, and here is a designation of the particular species, and the bottommost one is the ultraviolet continuum, which is characteristic of photospheric processes. So at the very top, you have X-rays, and then we have a far UV emission line, iron 12, which mostly parallels the X-rays. You can see the sun shows a strong cyclic variability in its X-rays, much stronger than any of the other UV emission lines, alpha Cyn A shows a similar variation. Alpha Cyn B, on the other hand, has quite a bit shorter of a period. You see, we've seen basically 2 cycles here and a much higher amplitude. And very curiously, Procyon here is basically flatlined. It shows a slow decrease. The degradation of the HRC sensor, which has been taken out in these plots.
2 minutes.
Now there's some bonus science here, and that is that we've been collecting these observations of the Alpha Centauri field for now more than 15 years. And here is a combined image from 10 years of 6 monthly observations. And you can see that there are many sources in the Alpha Centauri field, which is at low galactic latitude. So these are all stars. You see Alpha Centauri right in the middle here is a streak because it has high proper motion, and this is in a constant coordinate reference frame. Now, it turns out that these little rows here are individual snapshots of the 1910 kilosecond observations. Most of the stars in this field are variable. See, this one here is flaring. Here's one that flares, and this event right here is a super flare. This particular object is a red dwarf and white dwarf binary. Some of the stars show evidence of cycles like 6 and 10, and here's another flare. And you see the orbital motion of Alpha Centauri A and B, which is nicely captured by the high resolution of the HRC. So the bottom line here is that if you take an arbitrary observation of a field at low galactic latitude, so you're seeing stars, almost all the objects will be highly variable. And this brings us around to, how do we proceed in the future? And actually the future is now, and that is the eROSITA mission, which is carrying out 8 all-sky surveys with enough sensitivity to capture relatively bright stars over that period, perhaps to even see cycles, certainly to catch flares. Now, I noticed that, note here, I should say that Chandra in a 5 kilosecond observation with the HRC has a sensitivity of the cumulative 8 all-sky surveys, at least for objects near the ecliptic equator. So anyways, eROSITA is a future, and it's a very bright future. Thank you.
Thank you, Tom. That was a very interesting talk. We're going to save the Q&A for after the other speakers have spoken. I'd like to come back and ask you some questions about that in order to keep track with the schedule. We have one more speaker on today's session, and that is Abygail Waggoner. Abygail, can you start sharing your slides, please? Coming to us from the University of Virginia, and will speak to us about X-ray flares from T-Tauri stars X-ray flares from T-Tauri stars drive dynamic chemical evolution in protoplanetary disk.
Yes, very long title. Thank you for that. The chemical compositions that are available in exoplanets are determined by the chemical history within the protoplanetary disk phase. Rachel's talk earlier, I think, was a really great introduction for this. X-ray emission from the T-Tauri stars drives disk ionization, which actually leads to the formation of complex molecules. Now, these T-Tauri stars are known to be X-ray variable through flaring events, where the X-ray ionization rates in the disk can be temporarily enhanced. Therefore, X-ray flares can not only be variable in time, but also drive time variable chemistry within the disk. So within this talk, I'm going to highlight the short and long-term impacts of flares on disk chemistry. So we model flare-driven chemistry using an X-ray light curve generator, or XGen. XGen will be available on GitHub soon, but if you're interested in this model, please send me an email. So we take the light curve that is produced by XGen and we incorporate it into a chemical disk model with about 650 chemical species and 6,000 processes. So first I will explain the short-term variability that we see with the model. So flares can indirectly cause stochastic variability on days to week-long timescales and molecules that are dependent on disk ionization. So for example, flares can drive variability in water, as I showed in my 2019 paper. And in addition, they can also impact HCO+, where this movie is showing the relative change in X-ray luminosity over time on the left and the HCO+ column density on the right. And so as we advance in time, you can see that the HCO+ column density is temporarily enhanced when a flare occurs. So larger flares, like the flare just after 50 days, can increase the HCO+ abundance a significant amount. And this is a phenomena that actually has been observed before by Cleves et al. 2017. So these results suggest that some molecules can vary on days to week-long timescales. So next, I will highlight the cumulative impact of flares on disk chemistry over the course of 100 years. So here you can see the relative change in chemical abundances as a result of flaring, where a relative change of 1 indicates that a species is unaffected by flares. A relative change of less than 1 indicates the flares permanently decreased the species abundance, and a change of greater than 1 indicates that there's a permanent increase in abundance as a result of flares. Here I've only included changes greater than 5%, otherwise it would be very messy. So these results suggest that X-ray flares can contribute to a new chemical equilibrium or steady state over the course of decades to centuries. So just to highlight the conclusions, X-ray flares can drive time variable chemistry, which causes some molecules to vary on week-long timescales and causes a new chemical equilibrium. And both of these results are important because we can observe the chemical variability on these short timescales, and the long-term impact changes the chemistry available for forming planets. Thank you.
Thank you, Abigail, for an excellent and intriguing and interesting talk. Do we have any questions from the audience for Abigail? We do have one from Mario. Mario asks, if I am observing a star with disk and flares occur, how long does it take to have an observable effect on the spectrum?
On the spectrum. So it kind of depends on what molecule you're looking at. So with HCO+, it also depends on like what point in the disk you're looking. So it takes time for the light to actually propagate through the disk. So for example, the inner regions would be enhanced prior to the outer regions, but it is within like a few hours. So if you observed a flare and then immediately pointed at it with a radio telescope, within a few hours to a day, you would probably see the enhancement.
And Mario asks, can you say something about extreme ultraviolet and their effect on the disk chemistry?
Yeah, that's actually a really good question that I don't think I can quite comment on. I haven't explored UV at all, but that is something I would like to explore in the future though.
Great. And then we have an anonymous question. There were a lot of ions impacted. Are there any other types of molecules changed?
Yeah, so we do see that dominantly ions are impacted the strongest. There are a few neutrals that are exceptions to that. I'm still in the process of determining why exactly those neutrals are affected, but we are seeing some like simpler, smaller carbon chains that are being affected, along with, as I showed in a 2019 paper, water can actually be impacted as well, since it's dependent on, or X-ray flares enhance H3 plus abundance, which then produces more H3O plus, which then produces more water. So any species that are dependent on ionization could be impacted.
Awesome. Great. If we have any more questions for Abigail, I'd also like to open the floor to questions for any of our speakers in this session. If you have any for the previous speakers, please put them into the Q&A box. Tom, I had a question for you about the observing that you did on, that you showed us that the field stars in your area had lots of valuable, wealthy data, opportunities for extra science. And I'd like for you to talk about the observing plan that you use to acquire those targets and the time and how effective it's been in getting that long-term variability, and if you think we could build something similar for other targets.
Yeah, it's been kind of a struggle over the years, particularly with time constraints that Chandra has imposed because of heating of its propellant bay. However, these observations are needed only really twice a year because the timescales of the cycles are very long. They're decades typically, or even multiple decades. So the cadence is not very high, and thus you can sort of put these observations in the queue, just kind of fit them here and there, and so they're not a big impact on time criticality. I just mentioned that in the Alpha Centauri field, the low galactic latitude field, many of those objects that are detected are really quite faint. They have Gaia magnitudes. All of them are Gaia objects, but they have Gaia magnitudes that are like 16, 17, 18. So these are pretty faint objects.
Mm-hmm.
If we had a talk earlier by Stephen Chen, who showed some very hard sources that were not detected in the normal catalogs, and these likely are M dwarfs. Because most of the variable objects we see in the Alpha Centauri field, most of the flaring ones certainly are M dwarfs. These tend to have very hard spectra. But personally, I would like to see a long-term program, an observatory-based program that would capture semi-annual observations like I've been doing for Alpha Centauri for a number of objects just on a routine basis. And I've talked to a few people about this in the past, but the claim is that the Chandra only has a limited lifetime, so why should we institute a program now? But I would argue just the opposite. It looks like Chandra might run for a very long time, so now is really the time to put such a program in place.
Awesome. And I feel like the Chandra cooling targets call that we had would have been nice for something like this, except I don't think you could repeat the observations in that case. Right. And this would be calling for something where you could actually go back and revisit several of the fields.
Yeah.
Great. Thanks, Tom. We have another question for Abygail. How about the pH3 in Venus in response to a solar flare?
So I'm interpreting that question as asking, could a flare have enhanced pH3 in Venus when it was observed? And I don't know if I could quite answer that based on like the current research that I've done with this, just because the environment that I've been modeling and looking at is very different. I'm looking at a protoplanetary disk, whereas Venus's atmosphere would be a very different model. But as far as could a flare do that, I'm not entirely sure. I think we would probably know if a super large flare had happened. I think that I'm not entirely sure. I don't ever look at things within their solar system, but yeah, I don't know. It would be something cool to model at least.
That question was from Tong Bao. A very interesting question indeed. And we are in a solar low state, right? I guess, but we're still having flares occasionally. Okay. Any more questions for our panelists? Thank you, Abigail. I will wait a few moments before I thank our audience. Rachel points out that some of the biggest solar flares have occurred during solar minimum. Abigail, and it occurs to me that if these changes in the chemistry happen, they can be long-lived, and so it could still be past flares that create such things. Is that right?
So I think it also kind of depends. So based on the disk model, which again would be very different than like Venus's atmosphere, What I'm saying is that a single very strong flare doesn't typically have a long-term impact. Instead, that a single flaring event is what kind of is important for the short-term observational implications. It is the cumulative effect of many, many, many smaller flares over long periods of time I see that impact the overall chemistry.
Great. And we have one more question for you. Your talk has sparked a lot of interest, obviously. This is for Mario. Just to understand, you are considering effects on volatiles, not on molecules trapped in layers of grains or ice layers.
Yes, that is a good question. I definitely should have said that. Yes, all of the species that I showed were within the gas phase. Our model does include both gas and ice. And we do actually see some responses within ices, but not nearly as strong as the gas phase. And that's because the X-ray flares and the ionization rates from the flares are extremely lower along the disk midplane where the ices are the most abundant. So we dominantly see like the strongest responses along the disk surface where it's mostly gas phase. So yeah.
Great. Okay, if there's no further questions, then I would like to thank all of our speakers again in this session and remind you to join us for our next session, which is Stars, Disk and Planet Session 2, starting in about 1 hour. Thank you all for joining. Have a good day.
Thanks.